Hi everyone, today we are going to talk about reciprocal trig graphs. So we've done reciprocal trig functions, cosecant, secant, and cotangent, and now we're going to look at their graphs. So if you think back to the other day when we started with our with our sine graph, right? This was the general shape of it. 0, max, 0, min, 0, right? Out from 0 to 2 pi, that's one cycle. So your period there is 2 pi radians because that's how long it takes to complete one cycle. This graph just happens to go beyond that. But let's talk about what's actually happening with the cosecant graph. So remember that cosecant, and I'll write it down here, cosecant, remember, of theta is equal to 1 over the sine of theta. So if we were to take all of those values that we had in here for sine and do 1 over those values, that will give us the value for the cosecant. So I'll go ahead and write underneath here what those values were, right? We had 0, and then we had 0.5, and then we had 0.87, and we had 1, and then went back down, 0.87, 0.5, and then 0. And then went negative 0.5, negative 0.87, negative 1, and then negative 0.87, negative 0.5, and back to 0. So now if I do 1 over those amounts, that will give us the numbers to fill in this chart so that we can plot the points for the cosecant graph. Okay, so the sine of 0 is 0. If I did 1 over 0, if I did that in my calculator, right, if I did 1 divided by 0 in my calculator, right, I can't do it. It's an error because I can't divide by 0, which means there's no value that will be there. Okay, and anywhere else the sine graph is 0, the cosecant graph will be undefined. So I'm just going to put dashes in those spots. Okay, so now at 30 degrees, the sine was 0.5. So if I go ahead and I do 1 divided by 0.5, because cosecant is 1 over the sine, or 1 over 0.5. Oops, let me clear that out. Hold on. 1 divided by 0.5. And that's going to give me 2. So this value is going to be 2. Okay, and then I'm going to do the same thing, 1 divided by 0.87 with the next value. And that's going to be about 1.1 roughly, 1.1. And then 1 over 1, right, is just 1. So I can fill in the rest of these. 1.1, this is going to be 2. This is going to be negative 2. This is going to be negative 1.1. That was a negative there. This is going to be negative 1. This is negative 1.1. This is going to be negative 2. Okay, so I'm going to go ahead and plot those points on my graph here. So because it's undefined at 0, at pi, and at 2 pi, I actually can draw in asymptotes. And if you remember back, a vertical asymptote is whenever, right, you have a vertical asymptote whenever your denominator is equal to 0. We did that back last semester when we were talking about rational functions. So anywhere, and I'll do it out here too, just so you can kind of see the pattern here. Okay, so I know I have vertical asymptotes wherever the sine curve crosses the x-axis. The cosecant curve will have vertical asymptotes. Okay, so now let's go ahead and plug in some numbers here. I know that at 90 degrees, right, and that's going to be right here. This is pi over 2. This is 3 pi over 2. So I know at 90 degrees that my cosecant graph is also going to be 1. And at 3 pi over 2, or 270, is going to be at negative 1. And then this is going to be back here. Okay. I also know that at 30 degrees, I'm going to be somewhere up here at 2. So what is going to happen is this. Your graph is going to do this. So you're going to go there, and your graph is going to end up doing this. Should be a little more symmetrical than I made it, but hopefully you get the idea there. And then the graph here is going to go like this. So your cosecant graph is going to continue to do that as you follow the pattern of the sine curve. This is what cosecant is going to do. So it'll never cross those vertical asymptotes. It'll just be these kind of U's going in the opposite direction of the kind of U's of the sine curve, if you think of it that way. Okay, so if we talk about the domain, right, all of the possible x values that you could plug in to y equals cosecant x. Remember that sine curve was a nice continuous curve. There weren't any breaks. It was very fluid. The cosecant, because of the fact that it's 1 over the sine, that creates breaks in the graph itself. So our domain is that x can be anything except, so we can say this means x can be anything. That's an R. However, it cannot equal, that's an x there. It cannot equal multiples of pi, and that's what this k times pi means. So if you notice at 0, at pi, at 2 pi, this would be 3 pi. There's vertical asymptotes because it will never equal anything at those values. You can't do it. So x can be anything except at multiples of pi. Okay. Our range, when we talk about our range, and I forgot my little squiggly brackets up here. When we talk about our range, y is always going to be greater than or equal to 1, or y is going to be less than or equal to -1. And so a quick way we can write that is just the absolute value of y has to be greater than or equal to 1. So that is the cosecant graph. And now I'm going to take that same idea and we're going to look at secant. Okay, so secant is going to sort of follow that same kind of pattern. So wherever let me fill these in first. This is pi over 2. Here's 3 pi over 2. This would be 5 pi over 2. And so the same idea holds true, right? Wherever the cosine graph, because remember secant of theta or of x, whatever angle measure you use, is 1 over the cosine. So wherever the cosine is 0, the secant graph is going to have an asymptote. Okay, the secant will have an asymptote wherever cosine is 0. And we don't really even need to fill in this graph because I know that I'm going to do the same kind of thing that I did with the sine, and I'm just going to draw in my, that's supposed to touch there. Oops, I'm just going to draw in my kind of my U's of my graph here. And the same idea, right? It's never going to cross over that asymptote. Okay, so it's just going to be these U's kind of go in the opposite direction of the curves of the cosine. And so the only difference in the domain is where it falls. With the sine graph, right, the asymptotes were at multiples of pi. For the cosecant graph, it was at multiples of pi. For the secant graph, it's going to be at odd multiples of pi over 2. Right, at 1 pi over 2, at 3 pi over 2, at 5 pi over 2. And so the way that we write that is that for all x, x can be anything, and x cannot equal, this time we'll write it as 2k plus 1 times pi over 2. 2k plus 1 ensures that your number is odd. So 2k plus 1 is always going to give you an odd number, regardless of whether k is even or k is odd. Okay, so that just implies that odd multiples of pi over 2. And then again, our range, it's anything greater than or equal to 1 or less than or equal to -1. So we can say the absolute value of y is greater than or equal to 1. Now, the tangent graph is completely different from the other two, which is going to make the cotangent graph completely different from the other two as well. And so here's what's going to happen. Your tangent graph has this kind of shape. And again, I'm not going to go in and fill in the chart because I think you get the general idea of what happens with the chart. Remember that tangent is going to be 1 over the cotangent. And so what happens here is wherever this crosses the x-axis, I will now have asymptotes. So my asymptotes will now be here. Right, at multiples of pi. And where my graph did have an asymptote, it now will be 0. So there, and there. And my swishes, my tangent swishes are going to kind of change direction. Okay, so my graph is going to end up looking like this. It's going to go whoop, like this and come down like this. And then it will go this way. Oops. Oh, that's supposed to be more straight. I screwed up there. More like that. Okay. And my last one, oops, my last one will come down like this. And then that would continue on this way eventually. And it should be a nice, smooth kind of a swoosh. Clearly my swooshes aren't all that smooth, but you get the general idea there. And none of these values will you need to do an exact graph. I'm not going to ask you to plot the points exactly. I'm always really just looking for a sketch. Okay, when we talk about the domain, my squiggly bracket looks like a hot mess there. X can be anything again, except same as we had with cosecant. Multiples of pi would generate an asymptote. And then your range can be anything because the graph goes up and up forever and down into the negatives forever. So in this case, your range can be anything. So that is the difference between the reciprocal trig graphs versus the standard trig graphs that you've done already. Like I said, the cosecant and secant ones are very similar in nature. They just sort of follow the opposite of sine and cosine. And then cotangent, you just kind of flip the tangent graph around. Okay, again, none of the points have to be exact, just so that you have a general sketch of how it's supposed to look. All right, so that's all I have for you guys. We'll see you next time. Thanks, everybody.